Alright guys, so in this video we are going to discuss about how do I find Laplace transform of a solution of an ODE. Okay, suppose there is a ordinary differential equation with constant coefficient and I want to find out the Laplace transform of the solution. Okay, I'm not solving so far. I'm not going to solve for the ODE, but what I'm going to do right now is I'm trying to find out the Laplace transform of the solution. Okay, after you find out the Laplace transform of the solution, then you will be able to take the inverse Laplace transform. That's our goal. We will take the inverse Laplace transform to find out the actual solution. But for now, we are going to find out the Laplace transform of the solution. Okay, remember the formula from the last video? The Laplace transform of the second derivative is equals to s squared times Laplace transform of the y, and then minus, here is second derivative of y, right? So that is equals to s squared times the Laplace transform of y minus s at y at 0, s times y at 0, and minus y prime at 0. Okay, and what is the Laplace transform of the first derivative of y? That is s times the Laplace transform of y minus y0. Basically what we are able to do here is we are able to write the formula is about the Laplace transform of derivative of a function can be written as the combination of the Laplace transform of the original function and then their the initial condition at the derivatives lower than that derivative, right? Because here we have the derivative of y, the second derivative, but here is the first derivative and then 0 derivative, right? Basically y at 0 and then y prime at 0, but they are both taken at the initial values, and this is the Laplace transform. So this is kind of linear combination of Laplace transform of the original function and then the just the initial condition at all the derivative below that derivative, including the 0th derivative, that is the y at 0. Similarly, the Laplace transform of y prime is equals to s times Laplace transform of y minus y0, because the derivative below the first derivative is just y, right? And then add the initial value. Okay, so let us do this example. So we want to find out Laplace transform of y. So what is y in this equation? Y is the solution here, right? Because this is y double prime minus 10y prime plus 9y equals to 5t, right? And then y at 0 is -1 and y prime at 0 is 2. So we want to find out the Laplace transform of the solution here. So what should I do? I start with taking the Laplace transform here. Okay, so use the Laplace transform. What do you get? Use the Laplace transform. Okay, this is the curly braces on both sides. What do you get? If you use the Laplace transform on the both sides, you will get, so since the Laplace transform is linear, you can separate them, right? So you can do Laplace transform of y double prime, right, minus 10 times Laplace transform of y prime, right, plus 9 times Laplace transform of y equals to 5 times Laplace transform of t. You see that? So what is the formula for Laplace transform of y double prime? Just plug in that. So you will get s squared Laplace transform of y minus s times y0, right, minus y prime of 0. That is for the second derivative, right, minus 10. Let me write bracket there. What is Laplace transform of y prime? This is the second formula there, right? So you write s and then Laplace transform of y and then minus y at 0, right? And then plus 9 Laplace transform of y equals to 5. Can you tell me what is the Laplace transform of t? You're right, that is 1 over s squared. Now our goal is to solve for Laplace transform, so this is square there. Our goal is to solve for Laplace transform. So what I want to do is I want to factor this out or take the Laplace transform out from the terms that has Laplace transform. Okay, so if I take Laplace transform out, what is left here is s squared, right? Here is negative 10s minus 10s and there is plus 9. You see that? So that will be plus 9. So plus 9, right? And then Laplace transform, I'm writing that outside. So what is left is s times, what is s, y at 0, -1, right? So it is -1 minus, what is y prime of 0 is 2. So that will be -2. And then here you will see -10 times -y0 will be positive 10y0. But so it will be plus 10y0 is -1, right? And then equals to 5 over s square. You see that? Now you plug in those values and then you move, you plugged in already those, right? You move into the other side. Okay, what do you get? So you get s square minus 10s plus 9, and then there is Laplace transform of y, and equals to, what I'm trying to do is 5 over s square. So that will be negative s times negative 1 will be positive s, but if you move that to the right side, you will get minus s, right? And how about the other one? So you will get -2 and then plus 10 times -1 is -10. -2 and minus -10 will be -12 on the left side, but if you move that to the right side, it will be plus 12. That's what you get, right? So what is our goal again? Our goal is to solve for Laplace transform of y. So Laplace transform of y equals to, basically what you get is 5 over s square minus s plus 12 divided by, you divide both sides by s square minus 10s plus 9. What do you get? You get s square minus 10s plus 9. If you want to, you can further simplify, because in the numerator there is the one fraction there, right? So you want to write in the same denominator on the numerator fraction only. So if you simplify that, your final answer look like this: 5 plus 12s square minus s cubed divided by, you will get s square times the factor of this will look like s minus 9 and then times s minus 1. So this is basically the Laplace transform of the y in this problem. Okay, so again, our goal here, the final goal is basically solve this equation using the Laplace transform, right? So our first thing we will do is we will be finding out the Laplace transform of y first, and then later we will introduce inverse Laplace transform. When you do the inverse Laplace transform, that will cancel with the Laplace transform, and then you will have y equals to, and then you will have 5 plus 12s square minus s cube, the inverse Laplace transform of this thing, and then you will take the inverse Laplace transform of that to find out the final solution. Okay, that is our goal. But let us see one more example on this. Alright guys, let us look at another example. Okay, this example is similar to the previous one, so I just did it and then I'll just go over it. Okay, so find the Laplace transform from the ODE 2y double prime plus 3y prime minus 2y equals t e to the negative twice t. So the right hand side is a little bit different from the one that we just did. Okay, and y0 equals to 0 and y prime of 0 is -2. So what we do to solve this, so basically we want to find out the Laplace transform of the solution. Okay, so I'm taking the Laplace transform on both sides, so it will be 2 times Laplace transform of this plus 3 times Laplace transform of that minus 2 times Laplace transform and this one. Okay, Laplace transform of the right hand side. Okay, so what we do here on the next step is we'll plug in the formula for the Laplace transform of y double prime, that is s square Laplace transform of y minus y0 minus, oh, there is s, right? So okay, so when you take the Laplace transform of this, you will get 2s square because there is 2 in the front, so that 2 will be multiplied to all these 3 terms, right? So 2s square Laplace transform of y minus 2s y of 0 and minus 2 y prime of 0, that is the value of this thing, right? And for the first derivative, Laplace transform of the first derivative, there is 3s and then Laplace transform of y minus 3y0, right? And minus 2 Laplace transform of, this is Laplace transform of y. Now to find out the Laplace transform on the right side, you see that there is a product, right? So the main function is, you can think like this is like ft, right? And then this is e to the negative twice t. So you see that the Laplace transform of t is 1 over s squared. So the Laplace transform of ft is f of s. If that is the case, then the Laplace transform of e to the at times ft will be f, the right hand side, s will be replaced by s minus c. s minus a. If there is a, there will be f s minus a. But in our case, the main function is ft is t, right? The Laplace transform is 1 over s square. So to find out, if you multiply this t by e to the negative twice t, so s will be replaced by s plus 2. So that will become 1 over s plus 2 the square. You see that? So on the left side, what we do is you combine. This has a L Laplace transform of y, this has another Laplace transform of y, this has another Laplace transform of y. So I took that Laplace transform of y outside and then write the things inside, the remaining inside 2s square plus 3s and then minus 2. And then I move. So what is the value of this? What is y prime of 0 is negative 2, right? So this quantity is negative 2. So negative 2 times negative 2 will be positive 4, and I subtracted that positive 4 from the left side, and then that becomes negative 4 on the right. So this quantity is 0, right? So this quantity is 0 as well. So all the terms are taken care of here, right? So what we do next is let's find out the factors of 2s square and the plus 3s minus 2. So the factors of 2s square minus plus 3s minus 2 will be 2s minus 1 times s plus 2. You guys know how to get the factors there. So this is that factor. Now our goal is to solve your idea here is to solve for Laplace transform of y. So what I do is I divide by these factors on both sides. I get 1 over s plus 2 squared times 2s minus 1 times s plus 2. That's why we got s plus 2 to the third. You see that? And then times 2s minus 1 and minus 4 over 2s minus 1 times s plus 2. That's what you get. Okay, so we can extend or basically we can extend this formula to any derivative, right? We in the last slide we got the formula for nth derivative. What we do, if you have the second derivative, you start with s square ly, Laplace transform of y, and then minus, you decrease that by 1, so s to the 1, right? And then y 0, and then decrease this by 1, s to the 0 times increase the derivative, and you go up to the derivative that is 1 less than that derivative. If you have second derivative, you stop at first derivative here. If you have third derivative, you stop at second derivative. If you have fourth derivative, you will stop at third derivative, and so on. Let us see this example that has the fourth derivative in the differential equation. Okay, so see the differential equation has the constant coefficient on the left side. So what I'm going to do here is similar to the verb, but look at this. You have the value of y0, y prime 0, y double prime 0, and y triple prime of 0. So we need to know the initial value of all the derivatives smaller than this derivative. Okay, so I'm taking the Laplace transform on both sides. This is what I got for the first term, this is the second term, and on the right hand side you have that. Okay, so now I'm using that formula. So you start with s to the 4 because that is fourth derivative, Laplace transform of y, and then what we do, decrease this s cubed, and then y0. Now decrease this s square, increase the derivative y prime, decrease this s, y double prime, s to the 0, that is just 1, right? Y triple prime minus that 6 ly, Laplace transform of y is there. And what is the this is like, isn't this same as Laplace transform of e to the at ft, right? This will be, what is the formula for this? This is f of s minus a. Okay, now what I'm going to do next is I'm plugging in the initial values. This is 0, that is 0, that is 0, and that is 9, which is given there, right? So what I'm trying to do is I'm trying to take the Laplace transform of y out. So what is left is s squared minus 6. That's what, from this and that term, right? And then on the right hand side you have 1 over s squared plus 1, but this is 9, right? So negative 9 will go to positive 9 on the right hand side, and divide by s to the 4 minus 6 will give you 1 over s plus 1 squared times s to the 4 minus 6. I divided this by s to the 4 minus 6, and then divide 9 by s to the 4 minus 6. By the way, there is one small edit I made. I missed negative sign when I wrote the question there. Okay, so t e to the negative t. So that's the thing that I added later. Okay, so let us see that node. The Laplace transform is useful to solve an ODE of any order with constant coefficient. If the coefficient are constant, these values are constant, then you can use the Laplace transform to solve this. Okay, but so far we haven't solved it. We solved only for the Laplace transform of the solution, but later we will again take the inverse Laplace transform for that one. Okay, all right guys.